Okay, for what we have in the first problem of the Test 3 review handout, we're looking at solving differential equations through the use of Laplace and inverse Laplace transforms. And we have for number 1, okay, we have a second order differential equation, whereupon we have x double prime plus 4x is equal to 2. And we have the initial conditions that x naught is equal to 3 and that x prime naught is equal to 0. And just taking what we have in the terms and rewriting in terms of their Laplace transform equivalents. So we have for the Laplace transform of x double prime, again we have s squared times the Laplace transform x of s minus s times x naught, and again we have x naught equal to 3, and we have minus x prime naught, which is 0. And so we have for the Laplace transform, so we have s squared times the Laplace transform x of s minus 3s. And for the other terms we have in the equation, we have for 4x, the Laplace transform is equal to 4 times the Laplace transform x of s. And for 2, we have the Laplace transform of 2 is equal to 2 over s. And taking what we have and rewriting this equation in terms of the Laplace transforms. Okay, so again, so we have with x double prime plus 4x. Okay, what we have just in the setup. Okay, so I had s squared x of s minus 3s. So I kept the s squared and moved the 3s over. And you have plus 4x of s. And we have already 2 over s is on the right hand side. So in combining what we have with the terms, okay, so you have 3s plus 2, and writing 3s in terms of the fraction with the denominator at s, I have 3s squared over s, and I have plus 2 over s, so I have combining, we have s squared plus 4 quantity times x of s, and the Laplace is equal to 3s squared plus 2 over s, and isolating the Laplace transform variable x of s, we have 3s squared plus 2 all over s times the quantity of s squared plus 4. And setting things up along the lines of partial fraction decomposition, we have for this ratio, okay, we have a linear factor in the denominator with s and a quadratic factor in the denominator with s squared plus 4. So I have a over s plus, and you have the ratio bs plus c all over s squared plus 4. Again, we're maintaining a 1 degree difference between the factors in the denominator and what we have in the numerator. And just taking what we have and clearing out fractions. So we have in the makeup, okay, so I have 3s squared plus 2 is equal to a times the quantity of s squared plus 4 plus bs squared plus c times s. So we have 3 unknowns, and so I'll set up 3 equations. And I chose, along with 0, the values of 1 and 2, which I can plug in for s. So we have for the equations, okay, I have this particular setup, and writing what I have in terms of a matrix setup. So we have with a 3 by 4. Okay, first column is in reference to the a term coefficients. Second column we have with reference to b terms. Third column we have for the coefficients with the c terms. And again, we have first equation we have set equal to 2, second we have equal to 5, the last one we have equal to 14. And again, performing the reduced row echelon form. Okay, so I have a is equal to 1/2, b is equal to 5/2, and c is negligible. And so we have for the partial fraction decomposition, again, so a over s is transformed to 1/2 of the reciprocal of s. And again, c is negligible, but for b at 5/2, you're going to have 5/2 of s over s squared plus 4. And so we have with the Laplace transform x of s, I have in the partial fraction decomposition format, I have these ratios, and writing what we have in terms of the solution, taking the inverse Laplace transform and getting to officially x of t. So I have 1/2 of the inverse Laplace transform of 1 over s, and again, inverse Laplace transform 1 over s. Okay, so that is going to be at 1. And we have plus 5/2 of the inverse Laplace transform of s over s squared plus 4. And that's in the s over s squared plus k squared family, which will be in correspondence to the cosine function, which in this case with k at 2, we have the cosine of 2t. So we have for x of t, that is equal to 1/2 plus 5/2 of the cosine of 2t. Okay, for the second item, we have a first order differential equation whereupon we have x prime plus 4x is equal to 1, and we have the initial condition x naught is equal to 2, and writing what we have in terms of the Laplace transforms. Okay, for the first order derivative, we have s times the Laplace transform x of s minus x naught. So we have s times the Laplace transform x of s minus 2. Laplace transform of 4x, okay, we have 4 times the Laplace transform x of s. And we have the equation set equal to 1, and the Laplace transform of 1 comes out to 1 over s. And then we have, in looking at taking what we have in this equation, so we have for x prime plus 4x equal to 1, and writing what we have in terms of Laplace transforms. Okay, so we have x prime plus 4x is equal to 1, and we had the substitution whereupon we had the Laplace transform terms, and combining what we have in the Laplace transform variable x of s. I have the coefficients s and 4, and we have, in the case of 1 over s, that would be joined with 2, and writing as a combined fraction, again like 2, is going to be 2s over s, and joining with 1 over s. Okay, so I have 2s plus 1 over s, and then isolating the Laplace transform x of s. We have with division that we have equal to 2s plus 1 all over s times the quantity of s plus 4. And taking the partial fraction decomposition, so we have, upon clearing out fractions, we have 2s plus 1 is equal to a times the quantity of s plus 4, and we have plus b times s. So we have two unknowns, but we have as many zeros that can be applied. And if I negate b and solve for a, okay, we're going to have 1 is equal to 4a, and from this we have a equal to 1/4. If I take care of a and solve for b, so I can set s to -4, so I have that -7 is equal to -4b, and we had that b is equal to 7/4. And so with the values of a and b at hand, we're going to have for the partial fraction decomposition 1/4 of the reciprocal of s plus 7/4 of the reciprocal of s plus 4. So we have for the Laplace transform x of s, okay, we have this statement, and in solving for x of t, I'm going to be taking the inverse Laplace transform of this expression, and we have, once again, so we have with 1/4 the inverse Laplace transform 1 over s, okay, so I have 1/4 times 1 for the inverse Laplace transform of the reciprocal of s plus 4, okay, this will be e to the negative 4t. And so we have, in the follow through, we come out to x equal to 1/4 plus 7/4 of e to the negative 4t. All right, for what we have in the third item, we have a second order differential equation. And taking what we have in the terms, we have the Laplace transform and the second order derivative of x of t. And with the initial conditions as they are laid out, we now have s squared times the Laplace transform x of s. And we have minus s times x naught, where x naught is equal to 1, so we have minus s. And we have minus x prime naught, which we have at 2, so we have minus 2. For the Laplace transform of 9 times x of t, this would be 9 times the Laplace transform x of s. And for the Laplace transform of 0, that is negligible. And taking what we have in the expression, so going from the differential equation to the Laplace transform equivalent, and we have with our terms, okay, we have for the Laplace transform x of s expressions, we have the coefficients of s squared and 9, and go ahead and combine those together and move the s and the 2 over by adding and isolating what we have for x of s. I have s plus 2 all over s squared plus 9, and breaking up, we have s over s squared plus 9 plus 2 over s squared plus 9, and a little bit of maneuvering that has to be done. Okay, so we have for x of t, I had the Laplace transform of s over s squared plus 9, and again, this is going to be in the s over s squared plus k squared family, and we have k equal to 3, and this Laplace transform is going to be that of the cosine of 3t. And then we have plus the inverse Laplace transform Okay, so we have, to get this in line with the k over s squared plus k squared family, okay, we have, notice that 2 and s squared plus 9. 2 is not going to be k, so if I detach the numerator apart from the denominator, so we have 2/3, where the k value is going to be at 3, and we have a 3 over s squared plus 9. Now the inverse Laplace transform of 3 over s squared plus 9, okay, that would be the sine of 3t, and with 2/3 as a multiple, we have for the final outcome, we had that x is equal to the cosine of 3t plus 2/3 of the sine of 3t.